Thank you, Chairman. And thank you very much for inviting me this meeting. So this is very good opportunity to me to introduce you the LHD, one research field of LHD activity. So yes, so today I would like to give you the talk related to the investigation of the isotope effect. So in a fusion reactor, deuterium and tritium mixture plasma will be operated. So fusion reactor, So in a plasma, in fusion reactor, the prediction of the plasma property, we need the knowledge of the isotope effect. So nowadays, we, including the tokamak and the stellarator and the heliotron, we conduct the experiment usually one hydrogen isotope, for example, hydrogen or deuterium usually. So it is very important to compare the hydrogen plasma and the deuterium plasma, what is difference, why the difference occurs. So this is the purpose of this research. So in tokamaks, isotope effects have been recognized. So this is famous energy confinement time scaling. So this is theoretical, so scaling one, this is experimental one. And you can see this is expression of the scaling. Here, the mass effect exists. So the power is 0.19, so it is not so strong, but very important to know why such a mass effect appears. So, tokamak case, favorable mass dependencies have been observed in both L mode and H mode plasmas. So, lower energy confinement time, longer energy confinement time in deuterium, and lower threshold power for L to H transition in deuterium plasma. So, this is favorable. So, on the other hand, in stellarator heliotron, data set have been limited. So this is stellarator energy confinement time scaling, so ISS04 scaling. So you can see here, so no mass dependence is included in this scaling. So that is because stellarator heliotron community has not so, not have enough data set to make such a regression analysis. So this is one of the examples of the isotope effect study in stellarator and heliotron. So blue one is hydrogen and red one is deuterium, and this indicates the improvement factor of energy confinement. So Wendelstein 7AS, deuterium case a little bit worse, this case, but ATF and heliotron E confinement was a little bit higher. So anyway, in medium-sized helical devices, modest improvement of energy confinement time is observed like this, and but the data set have been limited. So in the large helical device, LHD, deuterium plasma experiment has been conducted since 2017. So this conference, so many Wendelstein 7X presentation, but LHD presentation is only one. So I would like to explain about LHD a little bit. So this is LHD coil configuration. So very different from the Wendelstein 7X. LHD case, the plasma confinement magnetic field structure is generated by a continuously winded helical coil, one pair of helical coils. And it is not seen here, but 3 pairs of colloidal coil also we have to generate the vertical field. And all coils are superconducting, same as Wendelstein 7X case. Okay, so So this is LHD. And plasma major radius is 3.42 to 4.1 meter. We can move by using the vertical field. And the plasma minor radius is averaged radius is 0.65 meter. And the toroidal field strength is less than 3 Tesla, so maximum 2.9 around. And we have 3 kinds of plasma heating device, so ECH, ICH, and NBI. And in our case, NBI is the main plasma heating device. So nowadays, the total heating power is more than 20 megawatts. And in LHD, we have divertor magnetic field structure. So it is not iron divertor, but helical divertor. So this helical divertor is equipped intrinsically. So this is toroidal cross sections, and they are cross section of helical coils. So you know, so magnetic field line surrounds the helical coil. So as a result, such a divertor structure is generated naturally. And as you can see, moving to the toroidal angle, toroidal direction, the cross section rotate like this. And can you see? So the divertor field line structure modified with moving to the toroidal direction. So as I said, so the divertor field line structure generated by the field line surrounding the helical coil. As a result, the divertor field line direction is almost toroidal. This is unique characteristic of helical divertor, different from the toroidal divertor in tokamak and the iron divertor in Wendelstein. Okay. So this is inside of the LHD vacuum vessel, and you can see such a snake-like structure. There, helical coil can. Inside this structure, we have helical coils. And between helical coils, we have divertor structure like this here. So they are diverter component. It is very difficult to see, but this is a dome structure of closed diverter. And both sides of dome structure, we have a diverter tiles, along the helical coil can. So the length is very, very long, And the material of the in-vessel component is like this. So diverter components are made of graphite. And first of all, we put first order panels like this, and their material is stainless steel, SUS316L. So LHD is a mixed material device, so carbon and mainly iron. Okay, and this is plasma. You can see the strong visible radiation is in the edge. Okay, so next I would like to move to the isotope effect investigation. So I would like to show you 4 regions isotope effects. So core plasma confinement and transport, and diverter properties, and plasma wall interaction, and the impurity transport in each plasma. First, I'd like to show the core plasma confinement and transport. So by the way, my main research field is diverter plasma physics and plasma wall interaction. So this talk is a little bit beyond my, ability, but I try to explain you. So 3 approaches to understand isotope effects on confinement we conducted. So first one is difference in the same heating power and the density plasmas. what's difference appeared. Okay. So by the way, first I'd like to show, explain you the transport characteristics. So usually, toroidal magnetic confinement plasma device, the transport is dominated by gyro Bohm scaling. So it is expressed like this. So gyro Bohm thermal diffusivity is Bohm thermal diffusivity times normalized ion gamma radius, like this. So this is this transport is dominated by tube turbulence. Yeah. And so if the plasma confinement LHD is dominated pure gyro Bohm, so then confinement should be degraded in deuterium plasma because of the such a mass dependence. So root mass dependence. So we conducted to confirm the property. So to conduct the comparison, DH ratio was changed in one experimental day. So to avoid the change of the heating condition or plasma wall condition. So during one experimental day, we could change the ratio, this ratio, from 1 to 0.35. Yeah? And this graph shows the time evolution of the deuterium hydrogen ratio for this one, the beginning of the experimental day and the end of the experimental day. You can see the beginning of experimental day, the ratio is almost 1, and at the end of the day, the ratio becomes 0.35. And I also show the ratio of helium. So we conduct the helium growth discharge. So inside the vacuum vessel, helium exists. So sometimes, but the helium ratio is less than 10%. Yeah. So for the same heating power deposition, ECH plasmas were compared in this study. So this is a comparison of the two discharges. So that is, one is, red is deuterium rich and blue one is hydrogen rich. So this is line average density. And you can see the, not just same waveform, but this gray hatched part, the density is almost same. And at that time, temperature is like this. So you can see this is a central electron temperature. Clear difference is appeared. So deuterium plasma electron temperature is higher than hydrogen plasma. On the other hand, central ion temperature is not so different between hydrogen and deuterium. So this is a turbulence, a line integrated turbulence measured by phased contrast imaging method. And this is for core plasma, and this is for H plasma. In both regions, the turbulence level is reduced in deuterium case. And we observe density and temperature profile at the gray hatched timing. So you can see the density case, deuterium plasma is more hollow compared to the hydrogen case. Yeah. And electron temperature, you can see the deuterium temperature is higher than the hydrogen temperature, but in H region, both temperature is almost same. That is also in density case. Density also they are in H region, they are almost same. Only a center part is different. Core plasma part is different. And this is pressure, and the ion temperature profile is almost identical. And this is a fluctuation amplitude. And also you can see the deuterium case, the fluctuation amplitude is reduced compared to hydrogen, especially in core region. In H region, it is not so largely changed. Yeah, this region. Okay. So the first approach, so difference in the same heating power and density plasmas, we get the result like this. Clear differences were observed between deuterium and hydrogen-rich plasmas. And in the deuterium-rich plasma, higher electron temperature and reduced turbulence were observed in core region. Okay, then second approach. So difference in the scaling law of normalized confinement time. So normalized confinement time is expressed like this. So normalized by ion cyclotron frequencies. So, so bomb-like and gyro bomb-like thermal diffusivity can express like this, and we can change the form like this using the rho and omega Ci and Q. Q in this case Q equal 1 because the hydrogen isotope. Okay. So and energy confinement time is scaled by thermal minor radius square over thermal diffusivity. Using this relationship, we get normalized confinement time like this. In bomb case, rho star is normalized ion Raman radius is times minus powered minus 2 seconds, and bomb-like powered minus 3. So normalized ion Raman radius dependence of experimental data can show the confinement is bomb-like or gyro bomb-like. And so the tokamak case and stellarator heliotron case, both the transport is gyro bomb-like. So it is shown by scaling law. So anyway, so the normalized confinement time is the same in hydrogen and deuterium plasma, in which the same rho star, so normalized ion Raman radius, if the confinement does not depend on mass. Okay, so let's see. So this is a result of the regression analysis of energy confinement time. So and the expression is like this. So this expression uses operational parameter. So mass and magnetic field strength and density and absorption heating power. And in this case, this expression, this scaling is very well express the experimental result. In this case, we can't see the mass dependence, nothing. But we modify this expression to normalized energy confinement time. Then we can see the two things. One thing is this confinement is gyro bomb-like confinement, transport is dominant. And the second one is mass dependence. Yeah. So the scaling of normalized confinement time shows the gyro bomb nature, and that suggests the ion Raman radius scale turbulence dominate transport, and also mass dependence appeared. Okay, so by the second approach, we get the knowledge that the scaling, normalized confinement time scaling shows the gyro bomb nature and mass dependence of LHD plasma. Okay, so then third approach. So difference in transport properties in dimensionally similar plasma. So this method is also used in tokamak. So by the control of density and absorption power and magnetic field strength, we can generate the dimensionally similar plasmas similar plasmas. So dimensionally similar plasmas mean same normalized ion Raman radius and collision frequency and beta. So in our case, P absorption power and density is modified, controlled, but heating power we had to scan. So, but as a result, we got such a dimensionally similar plasmas like this. In this case, so real plasma parameter is like this, but so normalized dimensionless, dimensionless, how to say, parameters like this, almost identical. So we compare these two shots, the transport property. So this is there is a result. So this indicates the thermal diffusivity of electron normalized by frequency. So in this case, in all area, so deuterium case, the thermal diffusivity of electron is reduced. And this is for ion case. For this case also, thermal diffusivity is reduced in the case of deuterium. So electron channel is improved significantly in deuterium plasma compared with hydrogen plasma. And improvement in ion channel is less than in electron channel. However, difference between in hydrogen and deuterium is still significant, like this. And we got 15 such a dimensionally similar discharges, and we get such a result. So horizontal axis is the normalized collisional frequency, and vertical axis indicate the difference of the thermal diffusivity. So if this value is 1, then it is pure gyre bond. And if the value is less than 1, that is shows some kind of difference of pure gyre bond. So in this case, you can see it is since the ratio of electron thermal diffusivity robustly stays below 1, and even lower than root 2, over 1 over root 2. And in ion case, thermal diffusivity shows collisionarity dependence. So the less collisionarity causes better thermal diffusivity, like this. So from the third approach, we got such knowledge that differences of thermal diffusivities of electron and ion between deuterium and hydrogen are evident. Okay, so next I'd like to present the diverter plasma and PWI. So what are isotope effects on diverter plasma and PWI? So in plasma transport in scrape-off layer, so mass difference can affect the transport. So because the flow velocity is proportional to the root mass. So if the upstream density and temperature is same in hydrogen and deuterium plasma, a diverter particle flux for deuterium plasma can be 1 over root 2 of that of hydrogen plasma. And what about perpendicular transport? Let's see. And the plasma wall interaction. So this is very evident that larger mass species cause larger erosion of plasma-facing components. So a larger radiation power can be expected. Okay, so this is physical sputtering ratio, rate of hydrogen, deuterium, helium. So becomes larger mass larger, the sputtering yield becomes larger. The chemical sputtering also has mass dependence. So larger mass species case is a larger chemical erosion period. So to analyze the isotope effect for divertor and PWI, a data set is prepared. So all discharges are standard discharge in LHD, and plasma sustained by NBI. And this is hydrogen and deuterium ratio, and this is also the helium ratio. So for deuterium case, almost 100%, and hydrogen case, so that is no deuterium. And I would like to show the medium case, mixture case also. So this is also data set explanation. So NBI heating power. So this is a data set. And this is a confinement property. So this is vertical axis shows the stored energy over plasma absorption power powered by 0.39. This is from the energy confinement scaling. So all data sets are almost same confinement. Yeah. So no difference between hydrogen and deuterium. So this is consistent with previous scaling. So operational parameters scaled by operational parameter, the mass dependence is not clear. So this is last closed flux surface density and temperature for deuterium and hydrogen and DH mixture plasmas. So in little bit higher density in deuterium plasma is observed, but temperature is almost same. And the total radiation in deuterium plasma is very high compared to the hydrogen plasma. Yeah? So this is density and this is radiation ratio to absorption power, about 2 times larger radiation power for deuterium plasma. But even such a different, such a big, larger radiation power, as I show you, confinement property is not so largely changed. So that indicates the radiation is, edge radiation is dominant. Okay, why such a large radiation occurred? So that is caused by carbon radiation. So this is C3 line intensity. Horizontal axis is line average density. As you can see, the deuterium case, the carbon emission is very large, and carbon 4 also. So this difference of the carbon content in plasma causes the large radiation difference. And it should be say that mixture plasma is between hydrogen and deuterium. So this is very reasonable. And I would like to show the same carbon-3 line intensity versus line average density. So this case, heating power is less than previous one, but this case I also show you the helium like this. So helium case, the carbon-3 radiation is very, very small compared to deuterium plasma. So as I said, physical sputtering rate is in helium case is largest in these three, but carbon-3 radiation is very small. This result suggests that carbon erosion is dominated by chemical erosion in LHD. And this is ion saturation current on diverter tile. We install the Langmuir probes so this is a little bit difficult to understand, but here is a mid-plane, in both sides mid-plane. And we put the Langmuir probe, we install the Langmuir probe in here. And this is ion saturation current versus line average density. So blue one is hydrogen. You can see low density area the both ion saturation current is almost same, but higher density deuterium case rollover occurred, but hydrogen still increasing. And mixture plasma case, little bit higher density, the rollover start to occur. And different point also shows similar property. So the rollover may not be attributed to changes of perpendicular transport, I think, because if the perpendicular transport changed, the different parts the plasma ion saturation current properties different from the this part. Sorry, this part. This is a little bit difficult to understand without detailed explanation. Anyway, we observe the rollover of the ion saturation current in deuterium case. So this is trial of reproduction of the H density and temperature profile in hydrogen and deuterium plasma with EMC3 iron code. So this is hydrogen case and this is deuterium case. To fit the H density and temperature profile, the transport coefficient is almost same between deuterium and hydrogen. And this is also the result of EMC3 iron simulation. This is ion saturation current at the diverter with laminar probe. And in this case, in low density area, both ion saturation current is almost same. But high density case, deuterium ion saturation current is larger than hydrogen case. This is different from, not consistent with experiment. So one reason is that carbon emission is not correctly considered in EMC3 iron. So we have to improve the calculation more. So last topic is impurity transport in H plasma. So this is again the carbon 3 and carbon 4 intensity against line average density. We observe the high, large, strong line intensity for deuterium case. And this part is carbon 5 and carbon 6. So this case also deuterium intensity is high, but the density dependence is very different from this C3 and C4 and C5 and C6. So this is because ionization energy. So C3 and C4 case, this is ionization energy is low, but the C5 and C6, the energy is very high. So compare with these two kind of line intensity, we can roughly consider the screening effect at the H plasma. So this is a ratio between C5 and C4, and so this density dependence is decreased to the high density. So this means the C5 decrease means carbon content in high temperature region is decreased. So this indicates screening effect more effective in high density region. Okay, and the screening effect compared to the hydrogen and deuterium, deuterium case, the screening effect is larger compared to the hydrogen. But anyway, so this screening effect, we have to consider more precisely. So that is future work. Okay, so let's summarize my talk. So I talked isotope effect at the core plasma and H and diverter. So in core plasma, we observe the favorable isotope effect and in core plasma transport and confinement. So for this favorable isotope effect, the unfavorable property of gyrobond, so that means unfavorable mass dependence is overcome by this effect. So as a diverter, in diverter deuterium plasma, larger erosion of carbon diverter types are observed. And diverter plasma region, we observe the diverter particle flux in deuterium plasma is similar to that in hydrogen plasma, especially in low density area. But with increasing the density, the ion particle flux roll over in the deuterium plasma case. And in H region, we observe the impurity screening is more effective in deuterium plasma than hydrogen plasma. Okay. So I still have a little bit of time. So this is not a scientific talk, but I'd like to show you. For better understanding of neighbors of the deuterium plasma experiment is necessary to conduct this experiment. So because the deuterium plasma experiment generates a neutron and a tritium, so the neighbors very be afraid of the such a radioactive things. So we have to explain very long time. So more than 10 years, meetings to explain to neighbors have been carried out in every summer and many places. And as a result, our ability to exploration is improved. So this is also the isotope effect on the slide for the explanation. So this is 13 years ago, so many characters, but nowadays it's very simple. So this is better for understanding for neighbors. Thank you.
Thank you very much. So, question, please. I don't know, maybe Eva first.
Okay. Could you go back to the presentation, because I would like the conclusions, because this is mostly.
Okay. So.
Okay. The main. There are two main questions I would like to pose. First one is when. Because you are showing that you have less flux of the, at least in high density, of the deuterium to the walls, and in the same time you are showing that the sputtering is larger. So when this sputtering was measured, in the low density plasmas or after the rollover?
Yeah, it's both. So this data is collected from the stored energy maximum timing. So various shots, not only one shot, but many shots. So all data is from the stored energy maximum timing.
One more thing, you say that the iron is not really working in your case, partially probably because of carbon, but is this code with already the molecular component or not, for hydrogen molecular component?
Yeah, yes, so I think, I'm not sure, but I think the molecular treatment is not so improved, I think, because, how to say, the detachment, so low temperature plasma is still difficult to treat by this code.
Yes, because as I know, in tokamaks explaining rollover without the, and also isotopic differences, without the molecular component doesn't really work. So if you did not incorporate the molecular part in this code, it probably cannot work. So it would be one more thing to take into account.
Possibly, but yeah. Our case, temperature is still several electron volts, so more than 5 electron volts. So yeah, so I consider that is the effect of carbon content.
Well,
radiation.
it may be that you are totally right, but explaining by temperature the lack of molecules is not really so, because if you have the high recycling regime, the molecules may not have the time to dissociate, even in high temperature. Okay.
Okay, Marcin?
Very nice presentation, thank you. And I start with the comment. I think the whole nuclear community could learn from NIFS colleagues how to work with local community in such a sensitive environment, as in Japan, to actually to work with people to start nuclear experiments. I think this is a great job you did, actually. I really admired it. I witnessed that. But my questions are, I have two questions. One is, when you saying about the screening ratio, wouldn't it be better to actually compare carbon 5 to carbon 3 or 2? Why did you compare to carbon 4?
Yeah, so one, so this is not a correct answer, but we didn't measure the carbon 2, unfortunately. So
Okay.
we have to compare these two lines.
Okay.
To analyze this property. Yeah.
Okay, so may I have one more question? If you observe that you have a higher intensity of the carbons, this of course should influence your onset of detachment. You probably should get easier into detachment, but it's also more difficult to control because you can go into the radiation collapse. So what's your experience here?
Yes, so yes, that is very natural consideration. I thought so, but result is not necessarily such way. So detachment is similar property. So that means similar occasion. So yeah, so we don't understand still now, and that is underway. Yeah.
Okay, maybe one question, please. Last question.
Yeah, thank you for a very clear presentation of the results. I think they're excellent. I just have one question of clarification. You showed in the erosion measurements comparing hydrogenic species with helium that chemical sputtering plays a large role.
Yeah.
And I think you also concluded that sputtering due to deuterium is significantly greater than sputtering due to hydrogen. Have I understood that properly? Would you expect such a difference in the chemical sputtering between deuterium and hydrogen?
Yeah. So yes. So this is an answer for you. The mass dependence of chemical sputtering will also exist.
Okay,
Yeah.
I missed that point. Thank you. Yeah.
Okay, then let's thank the speaker again. Thank you.